All right, you guys, sorry about all of that chaos with my technology in class today. My computer decided to crash. So, here's what we talked about. Open up your packets to page 18. We left off yesterday writing what we call longhand electron configurations. And so I believe the one that we wrote on page 18 was for antimony. And the configuration was 1s2, that's the first orbital that fills up with 2 electrons. Then 2s2, a slightly larger sphere, also with 2 electrons. Then the 2p6, which would be 3 of those p orbitals lying along the x, the y, and the z axis. 2 electrons in each, so that's a total of 6 electrons. Then the 3s2 and the 3p6, then the 4s2, and then next comes 3d10. So even though we're in the 4th period, as we fill up this D block, the principal energy level goes down by 1. So it goes 4s2, 3d10, and then 4p6, 5s2, 4d10, right, down in energy level for the D block, and then 5p3. That is a lot to write. The good news is that there is a shorthand method. This shorthand method involves finding the noble gas that comes before that element on the periodic table. So if I'm looking at my periodic table, if I look at antimony, I go up and over to the right to find krypton is the noble gas that comes before it. So I'm going to put krypton in brackets. By putting krypton in brackets, I have just taken care of this entire electron configuration all the way up to 4p6. So now I don't have to write any of that. If I want to write the shorthand for antimony, I put krypton in brackets, and then all I have to do is write what comes after. 5s2, 4d10, 5p3. Easy enough, right? Now, some people say, well, why can't you just write 5p3? Like antimony is the only element that ends with 5p3. That's a great question. The reason why is because we always want to show the valence electrons. And the 5p3, those 3 electrons are valence electrons, but so are the 5s2 electrons. We're going to talk more about valence electrons later, so you don't need to write this down. But in case you had that question, that's why, right? These are valence electrons and these are valence electrons. So that's why we would write everything that comes after the noble gas configuration. Okay. Now, there's another type of electron configuration that we write as well, and that is called an orbital diagram. An orbital diagram shows us all of the individual orbitals. This longhand or the shorthand, this doesn't show the individual orbitals. It shows the sublevels. What I mean by individual orbitals, you guys, is remember when we were drawing this yesterday, we said that the 1s was this sphere around the nucleus. That's an orbital. And then the 2s is a bigger sphere around the nucleus. That's an orbital. But then come the 2p's, which are a different shape, and there's 3 of them. Remember, there's the 2p that lies along the x-axis, the 2p that lies along the y-axis, and the 2p that lies along the z-axis. Those are 3 different orbitals in that p sublevel. We want to be able to show all of that. So instead of showing it with that sort of crazy drawing that I just did right there, instead, we show these orbitals, instead of like spheres and dumbbells and butterflies, we just write them as boxes. Remember the electron configurations we wrote into the boxes going up from low to high energy? Same thing. But instead of drawing them going up, we just draw them going across. So if we're going to do the orbital diagram for antimony, stick with this one. It's going to be kind of long, right? This is a long configuration, so we're going to write nice and small here. The first thing I want to represent is the 1s orbital. So I'm just going to do one box. That's the 1s. Then I want to represent the 2s. That's another box. And I don't even bother doing boxes. We just do lines. Next comes the 2p. Now remember, this holds 6 electrons. That's 3 individual orbitals 1, 2, 3. And notice how I'm putting my labels underneath. There are my 3 2p orbitals. Next comes the 3s. So I do one line to represent the 3s. Because remember, an S is a sphere. It just has one shape. It doesn't have a bunch of different orientations. Next comes my 3p. And the p's have 3 orientations. Right? They have the X, the Y, and the Z. Next comes the 4s. So I just do one line for the 4s. Next comes the 3D. Now remember, Ds have 10 total electrons, which must mean 5 individual orbitals. There are 5 different shapes. 1, 2, 3, 4, 5. That's your 3D. Remember those d orbitals? They look like butterflies lying on different planes. Let's keep going here. After my 3D comes the 4p. 1, 2, 3 for the p's. Then the 5s, just 1 for the s. My 4D is going to have 5 orbitals. And lastly, the p. 1, 2, 3. 5p. And now we just fill it up with electrons, right? So the 1s has 2 electrons in it. Remember, they have to have opposite spins. The 2s has 2 electrons in it, opposite spins. The 2p has 6 electrons. And get in the habit, you guys, of following that empty bus seat rule, Hund's rule, spread the electrons out before pairing them up. Back into the 3p, up, 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 down, down, down. You get the idea. Maybe you can even fast forward, or I can just talk and write faster. Up, 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 down, 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 up, down. We've got 10 here in the 4D. Down, 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 down. 5p3, 1, 2, 3. This, my friends, is called an orbital diagram. Okay, I want you to take a quick pause here, and I want you to practice this shorthand and orbital diagrams for the practice that you guys did on pages 19 and 20. I believe on 19 and 20 yesterday, I asked you guys to do the longhand, so that should already be done. Now take a break, go back there, and do the shorthands and the orbital diagrams. One last thing about orbital diagrams, actually, before you go. Even if they're not totally, even if a sublevel is not totally full, like, so for example, let's say we were doing nitrogen. 1s, 2, 2s, 2, 2p, 3. Oh, no, I don't want to do nitrogen. I want to do carbon. Carbon. 1s2, 2s2, 2p2. My orbital diagram would look like this. 2p. Up, down, down. 2 in the 2p. Up, up. This guy's empty. We still draw it though. Okay, so even if that sublevel is not full, go ahead and draw all of the orbitals in that sublevel. Okay, go practice and then come on back. All right. Hopefully you guys had no trouble with the practice there. Now that we're totally good to go on writing these configurations the way I taught you, it's time for some exceptions, right? And what I always say is nature does what nature do. You know, like we have these models to try to explain what we see in nature. But you know what? Sometimes those models need to be tweaked or adjusted. So there are 5 exceptions to the normal fill sequence. There's more than 5, but these are the 5 we care the most about. All right, let's write what we would expect to see for an electron configuration for chromium. Hopefully you're getting really good at these now. If you're confused, make sure you reach out and ask. 3s2, 3p6, 4s2, 3D, and then count over until you get to chromium. 1, 2, 3, 4. This is what we would expect chromium's configuration to be. Turns out, this is not what chromium's configuration is. In fact, one of these s electrons is over here in the D. Chromium actually ends with 4s1, 3d5. You're like, huh? Why? In fact, I could even write the shorthand for this, right? What's the noble gas that comes before chromium? It's argon. So put argon in brackets here. Make this a true shorthand. This is the actual configuration for chromium. And the reason why is as follows. It turns out that full and half full sublevels are more stable than almost, right? Than almost full or half full. Sometimes it's easier to look at a visual, right? So chromium 4s, 1, 2, 3, 4, 5, 3d. So this is what we would expect to see. But do you see how this is almost half full with 5 valence electrons? This electron, put it over here, and you get 4s1, 3d5. Half full, half full. Okay? So, right below chromium on the periodic table is molybdenum. Molybdenum does the same thing. Instead of ending with 5s2, 4d4, one of those pops over. Okay, so molybdenum will end with 5s1, 4d5. I'm going to show you guys one more example. Okay, so there are 5 of them, chromium and molybdenum. I know tungsten falls right underneath molybdenum, but it follows the normal fill sequence. So yeah, tungsten's not one of the next examples. Copper, though, is. Copper, silver, and gold are our last exceptions. Copper, silver, and gold. They are at the end of this period. 1s2, 2s2, 2p6, 3s2, 3p6. You would think it would end with 4s2, 3d9. This is what we expect. But that's not the case. In fact, copper ends with 4s1, 3d10. This is the actual. The actual. Why? Well, take one of those S's and put it over in the D, and look, you have a half full 4s1, which again, half full is stable, and now you have a full 3d10. Half full, full, more stable. Okay? So these are the 5 elements that don't fill up normally. They've got this sort of goofy thing happening where the 4s doesn't fill up all the way. Instead, we go to a half full D or a full D. Okie dokie. One last thing that we talked about in class were quantum numbers. Now you got to go back in your packets. I want to say it's page 16. I'm sorry, I don't have the packet in front of me. There is a chart on that page that talks about quantum numbers. Here's what quantum numbers are. I didn't really give you a spot for a definition, but you could just jot this down up at the top of your page. Quantum numbers are a set of 4 numbers that act as a tag or address for individual electrons. In other words, if I wanted to know every single thing that there was to know about this one electron that I just circled here in blue, I could give that electron 4 quantum numbers that tell me everything I need to know about that one electron. Okay? Now, I recognize that you're on a fresh page here, so you probably don't have that example anymore. So let's go ahead and write an electron configuration for a new element here. We can pick something nice and short. Let's go with oxygen. Actually, you know what? I want to go through the D block. Sorry, I lied. Let's do gallium so that we at least get through the D block. So find a place somewhere, you guys, and let's draw an orbital diagram for gallium. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. All right, let's fill it in with all those electrons real quick. For P1. Okay, so I'm going to just randomly pick an electron. Okay, like let's say I want to know every single little thing that there is to know about this electron that I just circled in blue. I just randomly picked one. You could pick any electron and assign it quantum numbers. The first quantum number that we assign is called the principal quantum number. The symbol we use for that is N. It represents the principal energy level, or the size of the orbital. Tells us how big the orbital is. The possible values, just like the Bohr model, are 1 through 7. Because these correspond, of course, to the periods on the periodic table. So if I was doing the quantum numbers for this electron here in blue, I would say that this electron has an N of 3, right? Because it's in the 3d orbital. The next thing I want to know about the electron is what shape orbital it's in, right? So it's in the 3rd energy level, but is it in the 3s? Is it in the 3p? Or is it in the 3d? The angular momentum quantum number, cursive L, tells us the sublevel or shape of the orbital. Gosh, my computer is making a really loud noise. I'll unplug it, see if that calms it down. Sometimes the fan gets really loud. I hope you guys can't hear it. Okay. So we know the different shapes, right? The different shapes are S, P, D, and F. But these are called quantum numbers, you guys, not quantum letters. So I need to give these letters a number value. So we say that S's have an L of 0, P's have an L of 1, D's are an L of 2, and F's have an L of 3. So yeah, the different shapes technically are S, P, D, and F, but when we give it a quantum number, we're going to go 0, 1, 2, or 3. So the L for this electron, it's in a D orbital, so it has an L of 2. So now I know, all right, well, I'm in the 3rd energy level, and I'm in this D-shaped sublevel, but there's 5 different options here, you guys, right? There's 5 different D-shaped orbitals. Is it in this one that's lying along the XY plane? Is it in this one lying along the YZ plane? What orientation orbital am I talking about here of these different 5? For that, we assign a magnetic quantum number, M sub L. This tells us the specific orientation of the orbital within the sublevel. And the way that we get that, the way that we assign those quantum numbers, is by making a number line underneath these orbitals. So a number line would have a 0 in the middle, and then a +1, and then a +2, and then a -1, and a -2. So just make a number line underneath. So for example, if we were doing the number line here for this 4p, I would put a 0 in the middle, a +1 here, and a -1 there. For s orbitals, you just put a 0 under them. Okay, so number line them. 0, +1, -1, 0, 0, +1, -1, 0, and 0. So for the possible values, you could just tell yourself, all right, we'll make a number line. Or technically, you guys, m sub l goes from -L to +L. So like m sub l equals -L to +L. So for example, with D, see how we had an L of 2? Do you see how our number line goes from -2 to +2, right? It goes from our -L, -2, to our +L, +2, right? So that's going to work out every single time because P's have an L of 1, so they're going to go -1 to +1. S's have an L of 0, so their m sub l is 0. So the m sub l for that electron is -1. It's just indicating which of those orbitals in the sublevel are we talking about. And then lastly, there's 2 electrons in there. So we have narrowed it down. We've gone from the 3rd energy level to the 3D sublevel to the -1 orbital within that sublevel. Which of these 2 electrons are we talking about? Got to talk about the spin. Upspin or downspin, which stand for clockwise or counterclockwise. And so for the values for an upspin electron, we use a +1/2. And for the downspin electrons, we use a -1/2. That's a downspin electron. Okay. Let's do one more. Or maybe you guys should pause. I just circled one in purple. Let's do the quantum numbers. Or you can pause it, try them yourself, and then check with me. My N would be 4. It's in the 4th energy level. My L would be 1 because it's in a p orbital. My m sub l would be -1 because I'm in the px orbital within the sublevel. And my spin would be a +1/2. Okay? And of course we can have zeros too, right? Like maybe I should have picked one in an S, right? Like let's do this one last one here in green. My N would be 2. My L would be 0 because it's an s orbital. My m sub l is also a 0 because there's only one s orbital. And my m sub s would be a -1/2. So no electron, no 2 electrons ever have the same 4 quantum numbers. It's like an individual tag. And that's it. So you guys have more practice that you can do. And I think it's on pages, let's see. This was page 18, and then you did practice on 19 and 20. I think it's 21 and 22, okay? So go practice on pages 21 and 22, more electron configurations, and check your answers. All right, you guys, sorry about that. And hopefully you don't have to stay up too late catching up after a bad tech day in class. All right, take care, you guys.